is a two-step process. The first one is transfer of information. But that's not enough. The students need to assimilate that information. They need to make sense of that information. I've often asked myself, where did number 2 happen for me? Where did it happen for you? Where did you go, oh, now I understand it? Did that happen while you were sitting in a room like this, listening to your professors? Yes or no? Did it happen for you when you were sitting in a room like this, listening? I see some people say yes and other people say no. So for how many people did it occur in the classroom? Show of hands. For how many people did it not occur in the classroom? One person. I assume that for everybody else here, it never happened at all. You never understood anything. Come on. Let me try again. For how many of you did it occur in the classroom? Raise your hand if it occurred in the classroom. A few in the back. For how many of you did it occur outside of the classroom? Okay. And what about the rest then? I think I should pick on a few people here in the audience and ask them to explain it. Huh? Oh, sometimes both. Okay. I would say that in the traditional approach to teaching, the focus in the classroom is on the transfer of information. And then students are sent home to do their homework and look at their notes. And that's when most of the assimilation of the information takes place. But if you ask yourself which of these two steps is the harder one, I think we all agree it's the second one. That's the one that we should focus on. That's the difficult part of education. The transfer of information is the easy part. The hard part is to make students go, oh, yes, I get it. So instead of doing 1 in class and 2 out of class, what we should really do is we should flip that around. We should do the information transfer outside of the class so that we can help our students with the much more difficult step 2. Now, there's a lot of discussion about step 1 out of the class right now. MOOCs and lots of things. Books, you name it. I don't want to talk about that. Because to me, step 1 is easy. I want to address the following question. If you have gotten to the point where students have taken responsibility for the transfer of information, then what do you do in the class? And the answer to that question is nothing new. It's teach by questioning. This is nothing new because 2,000 years ago, Socrates already said we should teach by questioning. In fact, Confucius also said that we should teach by questioning rather than by telling. For me, it was kind of an accidental discovery. Remember the question about the heavy truck and the light car? I was shocked by how poorly my students had done on that question. And my students were shocked too. It was the end of the semester. And 2 weeks later, we would have the final exam for the course. So my students were nervous because they didn't understand why they had done so poorly on the Force Concept Inventory, the FCI. So they asked me for a special session at night to go through every single question. So I booked a room like this. I had 250 students in my class. I booked a room like this at night from 7 p.m. to 10 p.m. And in those 3 hours, I went question by question through the entire FCI. And I remember coming to this question of the heavy truck and the light car. I thought, that's simple to explain, right? Newton's third law. So I turned my back to them and I made a drawing of the truck on one side and a drawing of the car on the other side of the board, and I drew the forces of gravity on each, and the normal force. And then I drew the force of the truck on the car, and the car on the truck, and I said, by Newton's third law, these two forces are equal to each other. And I could at once see that my students were confused. So I said, is there a question? They were so confused they could not articulate a question. You know how it is, right? If you're very confused, it's hard to articulate it. So I thought, this is serious. So I erased the board. And I thought, maybe that they're confused by the fact that the forces are the same, but the effect is very different. The reason the effect is very different is because of Newton's second law, F equals ma. Anyway, in the next 10 minutes, I managed to produce the most brilliant explanation you could possibly imagine. The entire board was covered with drawings and equations, and it was just fantastic, okay? After 8 minutes, I turned around, my jacket covered in chalk dust, only to see that they looked even more confused. And they were still not able to articulate a question. I didn't know what to do. I had tried for 10 minutes in 2 different ways to explain it to them. And, they didn't get it. I knew, however, that half of them had given the right answer. So in a moment of despair, I said to them, why don't you discuss it with each other? 250 students. Something happened I had never seen in my classroom. Chaos. They all started talking to each other. They forgot about me in front of the class. I could have walked away. They would not have noticed me walking away. But what was even more surprising was that in just 2 minutes, they figured it out. I thought, how can it be? I, the expert, the professor, tried in 2 ways for 10 minutes to explain it to them without success, and they figured it out in just 2 minutes? How can that be? But imagine you have 2 students sitting next to each other, John and Mary. Mary has the right answer because she understands it. John does not. On average, I won't claim this always works that way, but on average, Mary is more likely to convince John than the other way around. But that's not the important part. The important part is that Mary is more likely to convince John than Professor Mazur in front of the class. Why? Because she has only recently learned it. She still knows what the difficulties are that a beginning learner has. Whereas Professor Mazur has learned it such a long time ago. To him it is so clear that he doesn't understand the difficulties that a beginning learner has. I have a colleague, a very famous colleague, in the psychology department by the name of Steven Pinker. He has a beautiful expression for that. He calls it the curse of knowledge. The better you know something, not the easier it is to explain. No, the more difficult it is to explain to a beginning learner. So when I saw that, I thought, wow, I should use that in my classroom. So now when I teach, I don't lecture anymore. I tell my students, read chapter 22 before coming to class, or whatever chapter we're going to treat. So rather than me presenting the content of the chapter to them, I tell them, before you come to class, read chapter 22. I talk for a few minutes, and then I put a question on the screen. And then I give them time to think. It's quiet. We don't I don't want students even to talk to each other. Nothing. Okay? Silent. Then, after they've thought for a few minutes, I ask them to vote. Initially, we did that with fingers on the chest. Now we use these little clickers. Typically, I want between 30% and 70% of the students to have the right answer. Because in the next step, what I do is I tell them, find a neighbor who has a different answer and try to convince that person that you are right and he or she is wrong. I let them talk for 2 minutes, and then I poll again. If the first poll is between 30 and 70%, then this one is typically much higher. If it's less than 30%, in the first poll, there are not enough students to teach each other. Right? There are too few students who have the right answer. If there's more than 70% correct here, then there's not much to talk about, right? So ideally it's between 30 and 70%. And then we end with an explanation. Either I give them an explanation, or they can give an explanation. And then the cycle repeats until class time is up. And of course, the real learning takes place right there when the students are talking to each other. Let me show you a little video clip of how this works in practice. And we forgot to connect the sound system, so I'll use the microphone. So here we go. Let me show you a little video clip of how this works in my classroom. I'm going to have to show it from somewhere else. Just a second, please. So we have a rectangular loop that is placed in a uniform magnetic field in the direction indicated by these arrows. So the question is, what are the magnetic forces on the 4 different sides of this loop? So take a minute to think about this and then enter your answers. Okay, please enter your answers. We have a disagreement clearly here. So turn to your neighbor and see if you can convince one another of the correct choice.
Right. It goes out of the top goes in, so
Right.
they cancel each other out. There is a torque. There is a torque.
How do you know that?
I said torque. What did you say? But it happens to be a torque. Oh, so there's a way.
Initially we had sort of an even split. And now we have an absolutely overwhelming majority for choice number 2. So I don't show the initial distribution to my students, but I do show the second distribution, right? So they don't see the first distribution, they see the second one. Maybe you also saw that student go, oh, you could see the aha moment. You can actually see it happen in the classroom. You see students go, oh, I get it. You know, and once you have that, I get it, you know it for life. That's the beauty of it. Do you want to try it out? I think you look kind of tired there. So do you want to try it out? Yes? Okay. Did you all read? I had a handout with 2 paragraphs about thermal expansion. Did you read that? No? I'm joking. I'm joking. But you know, since you did not read before coming to my lecture here, I will need to tell you a little bit about thermal expansion. So thermal expansion deals with the fact that hard solids like wood or steel or concrete expand when it gets hotter, and then it contracts again when it gets colder. It's very important in engineering. For example, if you've ever been in a train at low speed, you may have heard this clickety-clack sound of the wheels as they go from one section of the rail to the other. And you may wonder, why do they leave little gaps that make this clickety-clack sound? The reason is that if you don't leave space and the rail expands, it gets longer, it will buckle, as you can see in this picture. The new big buildings that are being built downtown in Bangkok are built from steel beams. You need to take into account the expansion of the steel. The next time you park your car in a concrete parking structure, as you walk away from your car, look down, and you'll see that every 30 meters or so, there's a rubber strip. They make sections of concrete, and then they leave little gaps which they fill with rubber, because when it gets hotter, the concrete expands, and if you don't have that rubber that can compress, you have a problem. Now, the reason solids expand is they're made from atoms. I'm showing 9 of them here. And atoms get further away from each other when it gets hotter. So, this is cold, and this is hot. Cold and hot. That's all there is to it. You better pay attention there in the back, because I'm going to ask you a question about this in just a second. They're not paying attention there. They're going to be in trouble. Hey, you need to pay attention. Your neighbors are not paying attention. Okay. So, all there is to it is this, that cold and hot. Now, I'm not going to ask you about it, because you'll need to answer too. That's why I want you to pay attention. The reason atoms get further away from each other is that they're not sitting still. They're oscillating, they're vibrating. And the amplitude of that vibration is what we call temperature. So these are cold atoms, and these are hot atoms. Cold atoms and hot atoms. So as you vibrate over a bigger amplitude, you need more space, and you push the others away, right? If you were an atom, you wouldn't sit like this. You'd be shaking, and as you shake over a bigger amplitude, the people around you are going to have to move away. And it's not just those 9 atoms. It's all of them, the millions of billions of atoms that make up a solid. Cold and hot. Questions, anybody? I knew I was really a brilliant lecturer and that everything was clear, but you know, you better be careful, because I'm not going to hide this and then simply ask you the question, when solids get hotter, they expand because A, the atoms get further away from each other, B, the same distance, C, get closer together, because that would be me delivering information to you and you giving that same information back to me. I'm going to see if you can take this picture of atoms getting, this idea of atoms getting further away from each other, all of them, and apply that to a different context. So you better ask me questions, otherwise you're going to be in trouble. Cold and hot. I'm not going to continue until somebody asks me a question. Cold and hot. Come on. Cold and hot. Don't be afraid. Because if you don't ask questions, I will ask questions. Yes. Under the same blanket? Which people and which blanket? Yeah. Oh, I see. But I was talking about hard solids. Remember? Wood, steel, concrete. Okay? This is not a hard solid. It's a soft solid, right? So, I'm talking about hard solids. The wood, the stone, the metal. Any questions? Cold and hot. Are you fine? That's a very good question there. Why does the middle atom not move? Look at these. The middle atom here does not move. Why doesn't the middle atom move? I will tell you why, and you're not going to like my answer. The reason the middle atom doesn't move is because I made two drawings. I made this drawing, and I made that drawing. And then I put the two drawings on top of each other, and I put this atom on top of the gray atom underneath. But that's a choice. I could equally well have taken this black atom and put it on top of this gray atom. What would this atom have done then? It would have gone down and to the right. And this one would not have gone up, it would have gone towards the right. And that one would not have gone to the left, it would have gone down. The important point is not the individual positions of the atoms, because even with this other choice, they would all be further away from each other. It's the distance. Remember, in a real solid, there are millions of billions of atoms. So the position of any given atom doesn't matter. Very good question. Any other questions? If not, we're going to try it, okay? So remember the instructions. I'm going to ask you a question. You're going to think about it. You're not allowed to talk to anybody else. Oh, I guess people are afraid of my question. You're not allowed to talk to anyone else. Okay? If I hear you talk to somebody, I will come to you and put this microphone in your face, and you have to tell everybody what you just said. Then you can talk to each other. I will ask you to find somebody who's a different answer. So if you turn to the person on your right, and that person has the same answer, you say, thank you very much, and you turn to the person on your left. If that person also has the same answer, you turn to the person in front or behind. You have to find somebody who has a different answer. Okay, are the instructions clear? Okay. So here's the question. Consider a rectangular metal plate with a circular hole in it. Let's now imagine that we uniformly heat this plate. What happens to the diameter of the hole? Does the diameter of the hole increase? Does the diameter of the hole stay the same? Or does the diameter of the hole decrease? 1, increase. 2, stays the same. 3, decrease. No talking. Shh. Hey, those two there. If you talk, you're going to... they're not talking there. I'm going to give them the microphone. No talking. Okay. Okay. No talking. You'll get to talk in just a second. Shh. Who needs more time to think? Okay, so please vote. Choose 1, 2, or 3. Don't worry, it's, you won't get points or anything. So if you get it wrong, it's not a problem. But you have to press the button. 5 more seconds. 4, 3, 2, 1, and 0. So now find a neighbor who has a different answer and try to convince your neighbor of your answer. Okay? So go ahead. Find somebody who has a different answer. And if you don't talk to somebody, I will come and talk to you. So if I see you not talking, I will talk to you. Anybody who's not talking? What answer did you give? What about him? Oh, your job. Okay. Are you done talking? Well, and now you have the same? Good. See, check with other people too. Did you figure it out? Did you talk? Did you have different answers? So find somebody with a different answer.
I think we came out of the competition.
Yeah, of course. Yes, yes. Yeah. Good, good, good. Now look at this. You all got fired up. You're all talking. Hello? It's okay. Look at them. They're still talking about the hole. He hasn't even noticed that I started talking again. Imagine that instead of asking you the question, I would have given the same little lecture as I did before. And instead of asking you a question, I would have said, let's now apply this to rectangular metal plates with circular holes in it. If you take one of these plates and put it in the oven and turn up the temperature of the oven, the plate expands, and the diameter of the hole will... I'm going to keep you in suspense a little bit longer. You know, you would have been sleeping. What is more boring? What is more boring than rectangular metal plates with circular holes in it? Simply by taking something and instead of telling you, I